Good morning. I am honored here to have the chance to introduce our work. The topic of our paper is vulnerability testing on the key scheduling algorithm of present using deep learning. The outline of my talk as follows. First, I will briefly introduce the key schedule algorithm of present, which is the main object we focus on in this paper. Next, I will introduce the main task we do. Our goal is to retrieve the whole 80-bit master key from the last round key of the KSA of present. To achieve this, the first experiment, we try to use the multi-layer perceptron, simply called MLP, to fit the KSA. In the second experiment, we choose the residue network, simply call it ResNet, and train it as a classification network. Finally, a simple conclusion is given. Let's move on to the first part. The present cipher is a lightweight block cipher proposed in 2017. It employs substitution and permutation structure. So does its key schedule process. It has two versions, and we only discuss the 80-bit master key version here. The master key is loaded in the key register, and it iterates 32 rounds to generate 32 round keys. Figure 2 shows the key updating of one iteration. It includes rotation, S-box function, exclusive OR function. And finally, the most significant 64 bits are truncated from the key register at the real round key. In our first experiment, to retrieve the 80-bit master key from the 64-bit last round key, we try to fit the KSA and choose a basic neural network, multi-layer perceptron. We feed the network real 64-bit round key and want it to retrieve the master key bit by bit. The input layer contains 64 neurons, and the output layer is 1 neuron as a result. It has 3 hidden layers. And through our test, 30,000 training data and 4,000 testing data is enough to get a good result. That's about 80% bit positions can be retrieved at the probability above 0.9. For example, the 38th bit position on the right. It shows how its accuracy and loss rate change with epoch. And this table lists the best validation accuracy of each bit. We can see that from the 49th to the 64th, the accuracy is around 0.5. That means this MMP failed to learn its future or failed to predict these bit positions. And only the 49th bit has a little higher accuracy. It's above 0.6. And we found that these 16 bits are dropped out in the final key truncation after these rotations if we just ignore the S-box function in the KSA. To confirm this, we repeat the experiment on reduced round, and the result is the same, only the dropped out bit positions cannot be predicted. Further, we arrived at the conclusion that this MLP fails to learn the relationship between bit positions. That means it cannot fit the S-box function. So in the second experiment, we transform our main goal into a classification problem to distinguish the real master key from random data. So we choose the most commonly used CNN, the residue network. in the second experiment, because it has been already used to build the distinguisher successfully. The training and testing data are divided into two parts, with label 1 and 0. One sample with label 1 is 64 plus n bit in length. The front is 64-bit real round key, followed by n bits chosen from its master key. The rest labeled as 0 are random data with the same length. Through our test, 10,000 training data and 4,000 testing data is fine. Inconsistent with input data, the input layer has 64 plus n neurons, followed by 5 residue blocks with 2 layers each, and the kernel size is 3, the same with the neural distinguisher proposed by Aaron, and the following are 2 fully connected layers. And when we let n be 1, we found that the result is the same with the first experiment using MLP. For example, the group 1 from the table. Those dropped out bits are still hardly classified. And let n be 2. If we choose both bits among the 49th to 64th, the accuracy is around 0.5. But if we pick at least one bit outside, for example, group 2, 3, and 4, the accuracy rises above 0.7, and when n is greater than 2, the previous finding is still true. And let n be 16. We test every 16 bits in order. The accuracy rates are all above 90%. As a result, the classification network can learn the feature of XBox function, but it cannot directly retrieve each bit. So we combine the two networks for key recovery for practical use. We first retrieve 64 bits using MLP. It can get the result directly. And next, we train a ResNet that can distinguish n-bit real master key from random at one time. Finally, we go through the n's power of 2 and feed each to the trained ResNet to find the real n-bit sequence. The minimum value of the search complexity is 64, when n is 2 or 3. So in conclusion, for each MLP, the offline data we use to train it is about 15.97 power of 2. And for each ResNet, the offline data is about 13.77 power of 2. But the online process can be carried out within seconds on a modern computer. It is because the networks are pre-trained. And for a brute force attack, it needs 16 power of 2 data and 16 times KSA computation online theoretically. So the deep learning method costs less online computation time, but at the cost of more offline data. This drawback is also a significant feature of deep learning that relying on big data. And our work in this paper can be seen as a try to probe if deep learning can be connected with cryptography in different ways. In terms of vulnerability of KSA from deep learning perspective, The result is that MLP fails to fit the S box, but the classification network can identify it. Both of them is good at the rest linear part. We can use the findings to dig deeper, and it is likely to apply the method to similar cryptographic process in the future. Thank you for your listening.